So I guess we're rolling. Here it is. Whatever day we are into. For me, it's Wednesday, Tuesday, Wednesday. It's Wednesday, but I don't know what day it is for you guys. We're talking about continuity. I probably should just start this over again because I don't know what I was talking about for 18 seconds. But meanwhile, that out of the way. We're talking about continuity. I didn't have a catchy picture that reminded me of continuity, but you all know what continuous means. Continuity, continuous. So if you had to stop and think about what's the word continuous mean, you'd have some idea in your mind of what that particularly means. So mathematically, there's some conditions for something to be considered continuous or for it to have continuity. First of all, then we're talking about continuous at a particular point on its region, on the function itself. So for a function to be continuous, it's got to be defined at that point. The limit has to exist, and the limit has to equal the value of the function at that particular point. So three things to talk about. Function's got to be defined, limit's got to exist, and they've got to be the same thing. So we'll talk about, show you some examples of what that means. Okay. So this one is a continuous function. As we trace along, okay, if it's a function, why do we do that? Trace along, we've got the function, that piece of it, and it's a nice continuous function because anywhere I picked for point C, the function's defined. Okay, I don't have it on an axis, but I don't need to. Anywhere I pick, the limit exists. No matter where I go, even if I go up here, I'm heading to the same value. I've got no places where I've got any of the issues. And anywhere that I pick, like just say I pick right. Oh, all right, you want to lock up on me. What's going on? There we go. Oh, that's odd. I'm going to pick a point right here. Okay, right there. I do the function is defined. I do the limit, trace along from each side, same thing, and they're equal to each other. So that's a continuous function. This one's not continuous. Okay? And again, we're going to look probably right here as our suspect point. There's my value of C on the axis. So at this particular point, function's defined. It's defined by the black dot. Check. The limit exists. If I trace along from both sides, I get to the same whatever y value it is. The limit exists. Here's the rub. The limit and the function value are not the same, so we're not continuous. Got to have all three things be true for it to be a continuous function. Okay, we call this a puncture. So if there's a hole in a function, it's not continuous. I don't know if anyone needed that really spelled out for them, but mathematically that's why. Let's look at this one. Okay, another discontinuous function. And probably the place where you're wondering about is right here. Call that my C value. Is the function defined there? Yeah, that black dot. Does the limit exist? Okay, does the limit exist? Well, if I go from this side, I'm going there. If I go from that side, I'm going there. So the limit doesn't exist, and then since the limit doesn't exist, they can't be the same thing. So this one violates both places, so it's not continuous. We call this type of discontinuity a drop. So we've got a puncture, we've got a drop. So in order for a function to be continuous on an interval, it has to be continuous at every point in the interval. So if I have any breaks in continuity, then the function is not continuous on that interval. Okay? It's got to be continuous everywhere. Boom. Two types of discontinuities. We've got your removable type, and we've got your non-removable type. So, removable type, take a look at this one. If I look at what happens when x approaches 1, in this case, if I took the limit as x approaches 1, I get that 0 over 0 thing, the indeterminate form that we've been talking about. But, knowing what I know, I can factor this as x plus 1 times x minus 1. I now can cancel, and so I'm left with x plus 1, which is a continuous function. It's equivalent, that equivalent function that we're talking about, so it's a new function, g of x. But boom, we got rid of the discontinuity. We've got ourselves a removable discontinuity. Okay, let's look at this one. Okay, when x is equal to 0, what's going to be the problem? Well, we're going to get 1 over 0. That's a deal. Okay, deal breaker. Can I do anything to get rid of that 1 over x? Can I factor 1 into something else? Probably not. So this one is a non-removable discontinuity. Can't factor it out, can't remove it, can't get rid of it. It's a non-removable discontinuity. And where is it not removable discontinuity? At x equals 0. Okay? How about this one? Picture it. Something like that, forever and ever and ever and ever and ever. Is it ever discontinuous? No. So this one is always continuous. So there you are. Removable, we can remove them. Non-removable, we can't. Sometimes we have continuous. So then we get into this concept of one-sided limits. Okay? And the notation is a little bit different. You got to just really pay attention. The limit, the f of x, as x approaches c from below. Okay? So this means from below, meaning a value less than c. Okay, from below, so like from a lesser value, so from x that's less than c. Okay, this side means as x approaches c from above, or my x value is greater than c. Okay, so as I approach from below on this one, where do I go? Approaching from below, looks like I'm hitting that. As I approach from above, meaning my x values are bigger than the c value, it looks like I hit there. Boom. Okay? C from below, C from above. Below, above. So it turns out the limit is, no, we know that. We knew that we were going to have that limit right there. So a limit exists if, and this if is not spelled incorrectly. It means if and only if. Which means, when we say if and only if, means that the statement that I'm about to say works in both directions. A limit exists if and only if the limit as we approach from below equals L, and the limit as we approach from above equals L. So my one-sided limits have to exist, and they've got to be equal. Okay, that eliminates all the, all the stuff like we did this thing and that thing where we hit two different values. Okay, the one-sided limits both exist, and they have to be equal. So in order for the limit to exist, we've got to have that, that continuity that we talked about. The one-sided limits have to exist. They have to be equal. We look at the one-sided limits. Okay, let's just take a real stab at a one-sided limit here. The limit as x approaches 0 from above. So we approach 0 from above. We get closer and closer to 0, and we take the square root of whatever that number is that's really close to 0. If we approach from above, it's 0, right? Close to 0, take the square root, we get 0. If I were to look at the limit as x approaches 0 from below of the square root of x, what would I get? Take a number less than 0, try to take the square root of it. I think I'm going to have a problem, right? I'm going to get some sort of imaginary number. So if the limit as x approaches 0 from below of the square root of x doesn't exist. So does the limit ultimately exist? Does the limit as x approaches 0 exist? It does not exist because the one-sided limits aren't equal to each other. Ta-da! Okay? So, oops. Don't pause on that page. That's the work for tomorrow. Secret notes. All right, so where are we? We're going back through quick. We know what continuous meant when we started. We know mathematically what it meant. We know what things look like that are continuous, what things look like. We learned about punctures and drops and other things like that. Function is continuous on an interval. It's continuous at every point in the interval. So we can have functions be continuous for a little while and then stop, and then be continuous for a little while longer. Basic intervals. Removable and non-removable. I'm just repeating myself now, so I think that should do us. Thanks for watching. Hope you learned something. We're slightly under 10 minutes. Well done, Mr. Take. And if you have any questions, bring them with you. Talk to you soon. Thanks.